about the distribution of fitness effects. We'll tell a bit what it is, and how we can try to go from a bit more general assumptions and reduce them to a simpler model, which is a classic phenotypic fitness landscape model of Fisher's model, or other kind of landscape like that. So why bother about this distribution of fitness effects? So first, what it is if you take random mutations, whatever the nature, transposons, single substitutions, etc., and you measure the coefficient, the selection coefficient relative to the natural reference, which is the wild type, the parent for it, you have a given S, and if you do that on a set of mutants, you have a distribution of this S. And because mutation is really the ultimate source of variation, even when recombination acts on migration, they play on existing variation that is created by mutation. You can see that many models of evolution, maladaptation or adaptation, rely on, at some point on a model of how mutation affects fitness. And so because of its central role, it's been studied substantially empirically, and also in theory. So empirically, I'm showing a few examples. There are much more data out there, but I'm giving an example on purpose for single mutations, randomly produced within genes, so within given genes. So this, for example, is HSP gene in yeast in 4 different environments. And then this is 2 different genes in Salmonella, this is in yeast, measured again in 2 different environments. And there are some similarities and some complexities in those distributions. We could have expected anything because fitness is a very complex and integrative trait. And in spite of that, we see repeatedly some skewness towards negative values, always an excess of deleterious mutations, even if it's not 100% in some cases, and a kind of gamma-like shape, although. And if you can measure lethal mutation, which is the case here, or very strongly deleterious, you also have a whole class, often, of very strongly deleterious mutations, so kind of bimodal thing. And so there is reason to try to look for general rules describing that, because there are some similarities across several organisms and labs and stuff. So I can't go into detail on the many models that attack this problem. I'm going to talk of one of them. Basically, there are 2 kinds of classes. Ones are fairly general in their assumption, not relying on too much on mechanism, but they are then a priori less realistic because they don't detail how it works. And some are even much more detailed, like, for example, systems biology has several ones, like flux balance analysis, which I won't talk about, but it's a very nice, I think, approach, which is based on a lot of mechanisms, where you know all the metabolites in the cell, and you can predict how removing one enzyme from the whole soup affects the growth rate. But that depends instead then a lot on, you know the environment completely, the sugars, etc., you know your cells. So it's always like that. We're in a continuum from generality to precision. So I'm going to talk of one of them, which is a Fisher's geometrical model. That's because it's the original person who pinpointed it is Fisher, but it's really used also in a lot of evolutionary ecology. Whenever there's a model dealing with a changing environment through time, through space, many models we've seen before, they rely on this idea that there is an optimum, it's somewhere, it's moving or not, and there is variation on a set of phenotypes, and fitness is related to it by some curve function. So it's a quite widely used model, in fact. So here I give an example of an isotropic one, where directions are not all equivalent. So this is a set of traits. You have 2 here, but you can have n. And there's a function connecting these traits to fitness. So those traits are not fitness. They are, you could call them adaptation traits. They undergo selection for an optimum. And this function, therefore, has a curvature like that. And you have an optimal phenotype, which is here. You have your wild type parent, which is somewhere. And then you have a set of mutants, and they are characterized by having often a Gaussian distribution around the wild type and centered on the wild type, with the idea that on average mutation doesn't bias things. So from that, you can see how this can generate, so you can use that for many things, but you can use that to generate fitness effects of random mutations, because you have your wild type as some value of fitness, and any mutant has a given fitness here. So from assumptions on this, you can create a prediction on the distribution you get here of fitnesses. And those fitnesses are measurable empirically, and they integrate all the traits that are affecting it, which is a different approach from the quantitative genetics, which studies a set of traits that is known to have a strong effect. Here, we try to avoid this, to have the whole set, but to have less information on the actual underlying mechanisms. So, I'm obsessed with time, sorry. So, from that, there are several key assumptions that are made in that, an optimum for a set of n traits, so n dimension, here are two. Some quadratic or Gaussian fitness, there are many versions of this, but I'm going to talk about this one, which is mostly used in evolutionary ecology, and I think has received more empirical support. And mutation effects on phenotypes are Gaussian. So you see there are a set of fairly precise and thus strong assumptions. And this, so you can do more or less qualitative versions of that, but the more precise in assumptions you are, the more quantitative you are about the predictions you make on those distributions. So you do rely in several tests of this model, you rely on the quadratic function here, and you rely on the Gaussian here. And you may or not rely on the isotropy, both of this cloud or this cloud. So basically the question is whether it's circles or ellipse. Now the problem of that is even if you do test, and you talk about the results of the test, there is some frustration about the fact that the assumptions appear very simplifying, and so when you try to take this into an actual quantitative model of data, people, even if it fits or not, people are a bit shocked that this should fit anyway. And also, you don't really know what in this you expect to be quite robust and what you expect to change quite a lot across species or context. So that's a drawback. So the idea is to say, can we try to generate it from less strong assumptions? So basically, why it seems to work roughly and when. So more a way to justify the premises of this point. So the way I do that is I try to start from more general assumptions. There are always assumptions, obviously, but they are less precise, and they are more or less inspired from systems biology big conclusions or some data on mutation effects. The first one is huge pleiotropy. So that means here that any mutation will affect a lot of different traits initially. Those traits, I don't want to be precise about it. That's the point, otherwise you lose generality. But it's going to affect a lot of traits. So there are some justification, microarray studies, for example, on the effect of single mutations. Then I will assume weak and biased mutation that affect these basic traits and unbiased. Then I will assume phenotypic integration. This again is a bit inspired from systems biology in that we see that, for example, in metabolic flux balance analysis, you have many reflects, but in the end the growth rate is predicted from a few metabolites, a few much less, like ATP, NADPH, kind of hubs, if you will. So this idea I keep, and then I said that those traits in turn affect fitness, and that those, everybody is locally around a given optimum. So I do keep the optimizing idea. But we have removed anything about distributions or quadratic. So now, more precisely, I assume some genetic mutation. It affects some phenotypic network. Because this network is highly connected, like small world kind of thing, it has a high pleiotropy. So when you move one of them, it changes a lot of other traits. That's kind of a waving hand argument to justify high pleiotropy. And so there is a number of P for pleiotropy of mutable traits. These are the traits that are directly affected by mutation. And we're in a given genetic target. I don't precise what it is, it would be a gene. The target is defined by the set of places where a mutation will affect all those traits, not other ones. So the target is given by those particular traits. It will be the whole genome. Then from that, I assume a general distribution of effect and that they are unbiased. So on average, the dx, change in x, which are mutable trait, is 0. So that's the weak and they are weak effect. Then I assume some developmental function, which I don't want to precise, that goes from trait X to trait Y, so by something called developmental integration. These are my key metabolites, if you will. And those traits, therefore, those traits have also a mutation effect. And then finally, those traits directly determine Malthusian fitness around some optimum, to some function M of Y. Now from that, you can use several assumptions to get key local approximations. First, because we have a local optimum, locally we are under an optimum, you can use a Morse lemma, which says that basically you can play with the coordinates and turn them, expand them and turn them, so that there is a unique change of the reference. in which this function is in fact isotropic. It depends on distance. Basically, whenever there's an optimum which is called non-degenerate, so there is a second derivative, you can always approximate it's a kind of Taylor series. Then the second thing you do is you say, okay, I'm doing again a local approximation that my mutant has phenotype x plus dx on the mutable traits, and it's close to the, it's small relative to the wild type phenotype. So I can do again a Taylor series around the wild type phenotype. So then I get a linear relationship between the change in mutable traits and the change in optimized traits. This is actually the, I think, the block model by Wagner, which was not obtained like this, I think, but it boils down to the same thing. So the key thing then is your coefficients here, which are the derivatives of the function of integrating phenotype from x to y around the wild type phenotype. And those will drive the problem. So there are n times p. I call them pathway coefficients because they are pathways from the initial trait to the end. So from there, from just that, you obtain that because you have assumed a large number, did I say assumed a large? Yeah, high phenotype. So I assume a large number of initial mutable traits. So by a mere central limit theorem and the fact that you assume no bias in mutation, if there's no bias here, there's no bias here, and here by just a central limit theorem, you obtain the Gaussian. So you get one of the aspects of the Fisher model or quantitative thing from just a Taylor series that many traits integrate into a few. So you get this Gaussian. But of course then the question of isotropy will depend on the eigenvalues of that matrix, which is given here. So I will detail that. The other thing that you get is, if you remember from the Morse lemma, which you have set or function which is arbitrary to a particular coordinate system where it is quadratic. So we have the quadratic function and we have the Gaussian effect. But once we've done that, changing the coordinates, we can't change it again. So M is fixed now. We have to deal with it. It's not isotropic, it's different. So the last bit then is to study how, so here we get a non-isotropic Fisher's model. The last bit is to tell how the isotropy or not of this problem here. So basically, are the eigenvalues of that very similar or not? So here, to do that, you look at the eigenvalues of this matrix, which is basically a product of the coefficients, pathway coefficients, connected trait x to trait y, and V, which is the mutation covariance matrix between the original mutable trait. So those two things we don't know about. We don't want to tell too much about. And so the idea is to use a classic thing that dates back to Kimura. When you want to know, you don't want to know about things, you just assume they're distributed and you reduce the problem to an infinitely many to just a few parameters. So that's the same idea, but here for a matrix. So then you come up with, these are called random matrices. They're basically matrices made up by filling in random coefficients into that. So you can fill it, so this is the technical bit I switch. But using this random matrix theory, you can show that the eigenvalues of M corresponds to a known distribution. And basically, what comes up is that you have B, V, and B transpose V, B. And the thing is that if P is large versus N, all those different values, they come up to a few values here. So there's a kind of central limit theorem again. Many things cancel out, and you end up with a distribution of eigenvalues that is fairly close to each other. So that's an example. You don't, so as in the central limit theorem, you don't rely on many assumptions on what you fill it in. You can put Gaussians, uniforms, whatever. So here, for example, I put uniform, normal, or mixture in the elements of B, and you see this distribution of eigenvalues. So here, the red, the eigenvalues are very close to each other all along the matrix. Here it's more anisotropic, and that depends on a key coefficient, which is the ratio of P over N. So how many pleiotropic traits come to a few optimized traits. And if you add covariance in the elements of B, it just changes like an effective pleiotropy if you want. So the last bit is, now doing this, I've assumed that I was filling in my coefficients with a mean of 0. To be complete, you need to allow for the mean not to be 0. And when you do that, which I didn't expect at all, you end up with a very strong anisotropy coming out. So basically, because you have biased the coefficients, you end up having the same result as before. All the eigenvalues are stuck inside this Marsenko pasture, very isotropic. But there's one leading eigenvalue that goes up and up and up as the bias gets strong. So the only form of anisotropy you get in the end, when you've done the whole general options, is either you have like a ball like that, so everything is roughly the same, or there is one single driving direction and all the rest is the ball. In 3D you get that. So that's what you get. And so basically the idea is to say you can get this kind of Fisher model to emerge from local approximations around some optimum, integrating many pleiotropy traits into a few key traits, and and that's all basically. Close to an optimum and close to your mutants effect and so on. So that kind of does a clarification between what pleiotropy is, affecting many traits, and what pleiotropy is in Fisher's model, all those things about the cost of complexity. It's not the same traits you talk about. It can be fitted to DFE, so I give an example, or you can estimate actually this anisotropy part, so you can have access to this, how much, that's the data I showed you in the beginning. And there are, so you can wonder about what varies between contexts in this case, and there's an important part, I think, which is the problem of parallel evolution. So some modules, some targets, will have this shape because their coefficients are less. Some targets will be circles. And when you are in an environment for which you're selecting for that direction, then you will get parallel evolution along, so basically you will hit this module much more than you would expect randomly. But when you're in this environment, you will not hit it more than the others. So I think the interesting point is that it generates parallel evolution, which is obviously observed, but it's not always the same genes in always the same environment that generate that. Because that's also a fact that it's not always this gene that is parallel evolution. So we need both. It's not always the same, and it does happen. So that's, I think, the main qualitative point of this. I think I overstepped the time by a little bit. Take some questions.